Welcome to this week's unit, Validity of Research Results, Chapter 11. So we're going to spend some time in this unit talking a little bit more about validity. Recall from last time we talked about reliability, which has to do with consistency. Does your measure measure consistently over time and consistently within items? We can talk about reliability of results in the question of, do the results of a study replicate? Can you repeat the results of a study multiple times? Validity in terms of measurement, we talked about. Does your measure accurately measure the thing you're trying to measure? In terms of results more broadly, does the study actually produce correct inference based on the results? We also talked about confounding and extraneous variables. Now, initially, I had sort of made a distinction between these two things. An extraneous variable is something that is random, that is uncontrollable. A confound is something that is systematic, that is more controllable in your experiment. Your book sort of houses these things under the umbrella of extraneous variables and then makes the confound one version of an extraneous variable. The trick here is always that a confound is something that's systematic. A confounding variable is a plausible alternative explanation to your result. So, for example, we talked about this idea of observer bias and how important it is to keep observers blind to the hypotheses of a study. If all of your observers know the hypothesis of the study, that is a confound because any differences you see between your independent and dependent, between the levels of your independent variable could be accounted for by the fact that your observers are all aware of the hypothesis. It systematically varies with the independent and dependent variable. The way that we control extraneous variables, as I mentioned, is through random assignment, and the way that we control for confounding variables is by exerting experimental control. So making our observers blind to the hypotheses, and making sure that the levels of the independent variable are equal on everything in terms of the experience of the participant, except for that independent variable that we're manipulating. Now, in order to infer causality, in order to make causal claims, there are three criteria that need to be met: covariance, temporal antecedents, and internal validity. So temporal covariance is just there has to be a relationship between the independent and dependent variable. So if I think that remorse causes more forgiveness when someone apologizes, if I just ask people about level of remorse and level of forgiveness, there should be a correlation between those two variables. Temporal antecedents means that in time, the independent variable needs to precede the dependent variable. This also means if we're doing survey research, it is possible to do an experiment using surveys by manipulating various aspects of the survey. But if you're doing a survey, your independent variable must come before your dependent variable. The questions of your independent variable must come before the questions of your dependent variable. Otherwise, you have this problem of temporal antecedents. You can sort of think about this in terms of cause and effect. If the independent variable is the cause and the dependent variable is the measuring the effect, the independent variable has to come first in time. And then internal validity is your ability to rule out confounds and extraneous variables, and how strong of a case you can make that, yes, the differences we see in our dependent variable can only be due to our independent variable and not any of these other plausible alternatives. Now, when we talk about internal validity of research results, now we're not talking about measurement, we're talking about the results. This is the accuracy of your inferences. Is your study drawing an accurate conclusion? We can talk about this in terms of causal validity. Are you making did you construct your study well enough so that you can make a legitimate claim about causality? We can talk about causality in terms of description and explanation. Description is just an earlier phase of this explanation where we're saying, what is the causal relationship between these two variables? Study one identifies this causal relationship. Causal explanation, you can think about as sort of zooming out and saying, okay, when do we see this causal relationship happen versus when do we not? So, for example, there is a causal relationship between level of remorse someone conveys when they apologize and forgiveness. We might zoom out and then say, okay, when does this happen? Are there circumstances where it doesn't happen? Are there circumstances that can turn up the effect? So these would be moderating. Are there mediators? So for example, in the study that I did, we had a mediator that the perception that someone was unlikely to do this thing again in the future mediated that relationship between remorse and forgiveness. So remorse causes an increase in forgiveness through this third variable of this perception that they're unlikely to do it again. So description is just sort of the basic level. Here is this relationship between independent, dependent variable. And you think of the causal explanation as sort of adding color and texture and talking about when and where and specifically how this happens. Now, when we're doing quantitative experimental research, we're often faced with this question of, does X really cause Y? Does our independent variable really cause our dependent variable? Now, one way that we can design a study is with what we call a one-sample pre-post design. And this is probably what most students think about when they think about the most basic research study. We measure a group before, and then we administer some treatment, and then we measure the group after. So we might ask you about your cold and flu symptoms before. We might administer some antibiotics to a group of participants, and then measure their cold and flu symptoms after. And let's say we do this study, right? So we have this idea that we have a bunch of sick people. We measure the number of symptoms they have. How often do you have to blow your nose during the day? Whatever we measure, and then we administer some antibiotics, and then we measure their symptoms after. And let's say we support our hypothesis. We find that following the treatment, the number of symptoms decreased. Can we really say that it's the treatment that caused this decrease in the number of symptoms? And the answer is no, not necessarily, right? Because it's possible that the people who got the treatment might have just gotten better on their own. We have this confound of time, or as we'll talk about it, maturation. So one threat to internal validity in these kinds of one-sample pre-post designs is this idea of maturation, that the changes we're seeing in a dependent variable are not due to the independent variable, but are just happening spontaneously over time, right? Perhaps the antibiotics aren't doing anything. Perhaps the people have a virus, in which case antibiotics do nothing. But their body is fighting that virus, and even though the treatment actually has no effect, just because of maturation, because of time, they would have gotten better if we hadn't done anything in the first place. They appear to be better following the treatment. So one thing that we can do to address this threat of internal validity, this threat of maturation to internal validity, is to do what we call a between groups pre-post design and add a control condition. So now what we would do is we would take our group of people who are sick, and we would randomly assign them to one of two conditions. And we would measure their symptoms before. One group we would administer the treatment. The next group we would put on a wait list to get the treatment. That's sort of the ethical thing that we do these days. And then we'd measure their symptoms after. Okay, and this can help us to identify these maturation effects, right? Because this waitlist group is a control group. We can see what happens to this group of sick people over time without having this treatment at all, right? And so we can look at different results to figure out what's going on. So if we had some data that looked like this, and we asked the question, did the treatment have an effect? The conclusion would be no, the treatment really didn't have an effect. And the reason is the experimental group here, they decreased in their symptoms following the treatment, yes, but the control group also decreased their symptoms and they didn't get the treatment. So what we conclude here is that this decrease in symptoms, or this change in our dependent variable, is got to be due to maturation. It's not due the treatment itself. Now, on the other hand, if we had data that looked like this, so the experimental group is getting much better following the treatment, and there's not as much change in the control group, then this difference here, we can say, yes, this is due to the treatment itself. So adding this control group helps us to rule out this potential threat to internal validity, this potential confound of maturation. Now, there's another threat to internal validity that we can encounter that we refer to as regression to the mean. And the idea about regression to the mean is that extreme scores generally become less extreme over time. And the reason for this is that randomness is what makes them extreme in the first place. And this is particularly problematic if we're selecting participants based on some kind of score or some kind of input. So if we measure, if we have all the students come into our assessment center and we assess their level of reading proficiency, and we select students who are doing very poorly on that assessment in reading for a special intervention program, this can be problematic. So if we select based on reading scores, so the really, really bad readers and the really, really good readers, and then we give the really poor readers the reading skills program and the really good readers no program, and we measure these results, we will potentially have a problem with regression to the mean. So if we ended up with these data, and we're asking the question, did the treatment have an effect? It seems like, yes, the reading skills program did better. And even the kids who are good readers showed some improvement without intervention. And so they might have both improved with the reading program doing better. But what about this result, right? What if we saw that the no intervention group stayed about the same and the reading skills program improved? Well, the problem here is that we can't know whether or not the improvement is due to the treatment, or if it's just simply regression to the mean. If the scores are just getting less extreme over time and the treatment isn't what's causing this change. So how do we fix this? The way that we get around this is with random assignment. So if we're going to use scores we're going to use extreme scores to select participants. Okay, only people who fall below this threshold are going to be included in our intervention program. Then what we need to do is we need to start with that group of extreme scoring students and then randomly assign to conditions from that group of students. So we have poor readers in the experimental condition and equally extreme poor readers in the precondition, in the no intervention condition. And this way we can rule out potential regression to the mean. So if we end up seeing something like this with both groups equal here, we're going to see both groups increase a little bit, and this increase for both groups is regression to the mean. But the difference between the two groups here, if this difference is significant, what we can say is that this improvement from here to here, this is the treatment effect. And this improvement from here to here, this is just regression to the mean. In contrast, if we see both of our groups just improve over time, right? So they're both randomly assigned to the treatment or control condition from a population or from a sample of very poor readers, and they both just get better, then we can know that this is likely a regression to the mean. Now, when we talk about statistical validity or conclusions of statistical validity, it's important to remember that anytime we're doing statistical analysis with quantitative data, we're making probabilistic judgments. We're looking at the strength of the relationship in terms of the effect sizes, which we'll talk about. But really, at the end of the day, any conclusion that we make using statistics is probabilistic. We're saying this is very unlikely, and so therefore there must be it is more likely there's a significant effect. But we're still allowing for the possibility that we could be wrong. So statistical validity is really about the probability that we are wrong. Okay. When we do a statistical test, and I promise we're not going to get too into statistics here, but it's important, especially as you start reading more and more research, primary source literature, it's important to really get an understanding of what this p is less than 0.05 business is. So when you're conducting a statistical test, the question you're really asking is, what is the probability of our result? Right? If we're talking about association or correlation, we're saying what is the probability that there is no relationship? For causal claims, we're asking what is the probability that there is no causal effect of X on Y? Now, hopefully you have heard of P is less than 0.05. And what P is less than 0.05 literally means is that this is the threshold that we have decided as scientists that we will accept a chance that we are wrong. So if I find a relationship between remorse and forgiveness in my study, P is equal to 0.05, then what that statement means, that P is equal to 0.05, what it means is that there is a 5% chance that relationship, that significant relationship we got, happened randomly. It's just random chance, right? There's a 5% chance that it's random and a 95% chance that there is some relationship between these two variables. Or there's a 5% chance that the causal relationship we observe is random and a 95% chance that it is true, and I'm doing air quotes, truth with a capital T. So you can think about this P is less than 0.05 as sort of like the probability that we are wrong. Okay, and when we make conclusions, we come up with statistical conclusions. There's always a chance that we're wrong because these are probabilistic judgments that we're making. So we give special names to these two ways that we can be wrong. So a type 1 error is when you find a significant relationship even though it is not true. And I have here, AKA God speaks to us, because you can never know whether or not it's true or absolute truth. But you can think about this type 1 error as a false positive, right? So you can think about a male going into the doctor to get a pregnancy test, and the doctor comes back and tells this young man, I have found that you are pregnant. Okay, this is a false positive, right? You find a significant effect even though it is not true. Okay. Now, a thing to know about p-values is that the smaller that p-value, the smaller the chance of making this type 1 error. So p is equal to 0.001 means that there is a 0.001 chance that your study made a type 1 error. Okay, finding a significant result even though it is actually not true. Okay. The other side of this coin is the type 2 error. This is when you find a non-significant result even though it is true. Okay, and you can think about this as a false negative. So this is when you do your study and you do your data analysis and it comes out there's no significant effect of X on Y. There's no causal relationship. There's no correlation. But in truth, again, truth with a capital T, there is a significant relationship that exists out there. You just happened to not find a significant relationship in your study this time around. You can think about a type 2 error as a false negative. The very pregnant, 9-month pregnant woman, she's very obviously has a baby in her uterus, goes to the doctor's office, and the doctor takes a test, pregnancy test, and says, guess what? You're not pregnant, right? That's a false negative. The test is wrong because the woman is clearly very pregnant, okay? So anytime we're dealing with statistical validity, we're concerned with this p is less than 0.05. And because of this, this is yet another reason why, as scientists, quantitative researchers, we're very interested in this idea of convergence of data. No single study makes scientific truth. Just because one study publishes one result doesn't make it true, because there's always the possibility that that one study is just a type 1 error. It's just that one random time when something is significant, and 15 other people did 15 other studies, and they all got non-significant results that weren't published. Okay, so when we're thinking about research, this is why we're so concerned with convergence of data. If you have 10 different studies done by 10 different researchers that all show a significant effect of X on Y, we have much more confidence in that than a single study on its own. Now, whether or not we get statistical significance has to do with these two really big ideas in quantitative research, and that is power and effect size. Statistical power is your ability to find a significant effect if it exists. So if you imagine in a small scale simulation that there is an effect of X on Y, right? So we have some, modeling data. It's not real. We made it up, and we know that there is an effect of X on Y in this model data that we made up. Power is your ability to find that effect. So the analogy that I like to use, that I must admit I didn't make up, I borrowed from a textbook, but it's a great analogy, is that power is your flashlight. Imagine that you're looking for something in a pitch black room, and power is the flashlight. Power roughly equates to sample size. Okay. The bigger your sample, the easier it is to find what you are looking for. The brighter your flashlight, the easier it is to find what you're looking for in this dark room. Okay. If you have a huge flashlight, if you've got a huge sample of 3,000 people that's representative of the United States population, then you have a really high amount of statistical power, right? If you are looking for an effect of X on Y and you have a really highly powered study, then chances are, if it exists, you are going to find it. Okay, this is your 3,000 candle power military grade flashlight that can put a spotlight on the moon, right? Really high power. If you're using a university sample that's not representative, or you are using some very tiny sample, this is sort of the akin to a Motorola flip phone from the 90s. You're in the dark room and you flip open your screen and you've got this little glowing screen that you're using to look for. So a really tiny sample is going to have low power. It's going to make it harder to find that effect if it does exist. Okay? So that's power. Effect size, on the other hand, is the strength of the phenomenon. Right? It's the magnitude of the relationship between X and Y. It's the size of the thing that you are looking for in that dark room. Okay, so power and effect size work together. If you are looking for a gigantic effect, so you're in that pitch black room and you are looking for an elephant, the Motorola flip phone, that little tiny sample, is probably going to be enough for you to find that elephant because it's huge, right? You don't need a lot of power to find it. If you are looking for a diamond earring that you dropped on the floor in this pitch black room, then you're going to need a much bigger sample size to find that smaller effect. Okay, so power and effect size work together, and they affect the statistical validity of your results. Right? If you have a very huge effect, you should be able to find that effect with a very low power, small sample study. If you have a small effect, you're going to need a bigger sample, higher powered study in order to find that. So hopefully that makes sense and I didn't freak you out too much about talking about statistics. Now, when we talk about validity in quantitative research, we can talk about it in terms of descriptive and interpretive validity. So descriptive validity is just sort of the factual accuracy of your account. So are you accurately representing the information that you are gathering from your participants, whether you're doing an interview or you're doing a focus group? Is this factually accurate? So one way to get this descriptive validity is to have more than one investigator collect and interpret the data. You can think about this as analogous to inter-observer reliability in quantitative studies. If we have two people who are listening to the same interview and drawing the same conclusion, then we can say that we've got some descriptive validity in our qualitative research. Interpretive validity has to do with, are we actually getting the meaning that the participants are trying to convey? Are we accurately interpreting what they're saying? And one way that we can go about verifying this is with participant feedback, or they call this member checking. So periodically stopping, rephrasing the participants' words, and feeding it back to them and asking them, so it sounds like you're saying this. Are you saying this? And then the participant says, yes, that's what I'm saying. And so you're getting confirmation that you're interpreting this qualitative data correctly. Now, when we talk about external validity, which we've talked about before in terms of quantitative research, external validity is not really necessarily a goal of qualitative research. More often than not, people and settings are not randomly selected. And so you can think about qualitative researchers are more interested in documenting what's going on in a particular setting versus drawing broader conclusions about what might happen across settings. You can think about qualitative research almost as being like almost it's sort of akin to journalism. We're trying to gather information that describes a particular set of phenomena in a particular context. Okay. Qualitative research can be used to make generalizations, to similar situations, and where we might expect these things to replicate. But generally speaking, qualitative research really isn't interested in this question of, or this concern of external validity. So generally, when we're talking about validity of qualitative research, we're about the trustworthiness and the credibility of the results. And one problem with this is researcher bias. This is sort of finding what you are setting out to look for. We talk about this in social psychology as confirmation bias, this idea that people actively filter information in such a way where they only pay attention to information that confirms their existing beliefs, prescriptions about society, and ignore or discount information that disconfirms their existing beliefs. Your book suggests that a key strategy to reduce researcher bias is reflexivity, self-reflection about your biases. What are my biases? And how can I be more neutral or fair about these things? There's a huge assumption here that people are aware of their own biases. And this is problematic. I sort of disagree with this idea that it is possible to self-reflect about our own biases, because many of our biases are implicit. They are unconscious biases. And because they're unconscious, we are inherently unaware of them. And so that makes this sort of reflexivity strategy problematic. Not to say that this isn't important. Again, people should think about their own biases, but it's also important to know that many biases are implicit, and because we're unaware of them, they still influence our behavior outside of our conscious awareness. So that's it for this week's unit. As always, you can email me if you have any questions.